So I'm going to tell you about some of the recent work we have been doing, which is relevant to modeling human behavior and model fitting. I thought this is the most appropriate for this workshop. So the title may not sound very. Oops, I dropped it.
I can take care of that.
Okay, so the question we are looking at is that basically we are looking at learning problems and how we learn in, let's say, naturalistic environment. There are two big issues about real world learning. One is that, and I argue that the learning is not enough; it needs to be constantly adjusted. So even though it sounds counterintuitive, you think that learning is a process that you update things. And I argue that actually you need to update that updating process constantly. So one reason is that the real world is multidimensional and it's constantly changing. So this is just to make you a bit happy about the situation we are right now, but right now actually this is from 10 years ago. Right now the political situation is, this looks like a joke to compare what we have right now. But anyway, so there are two aspects, multidimensional and changing. So one thing that you need to remember is that the action we choose or any option you choose, sorry, an action you take have many features. It's not clear what feature determines the outcome. So for example, you eat certain food and you enjoy it or not, it has many components. You choose anything in real life and you don't know what feature of that thing is actually most rewarding or most important. So what I mean by the multidimensionality of the real world options is that each option has many features. And it's not clear, it's not obvious what features actually determine the reward outcome. So I have this example I forgot about. So imagine you meet somebody new in a meeting, and what actually determines a good conversation, good interaction, is it for your future is all these components, a mixture of them, but you don't know. What actually would determine a good conversation, good interaction, good network? This is the situation with many types of decision making. Another problem or difficulty with learning in real world is that, which requires adjustment, is that the association between cues, outcomes, and reward constantly change over time, and that can happen at different time scales. So this is a cartoon of. So basically, if you want to know the value of anything, it's equal interaction with somebody, choosing some option, eating some food over time. You cannot rely on one outcome to determine the value of something. You have to integrate the outcomes over time, and that's what we call integration of reward. So this is this is an analytical thing, happy face and sad face. This is your interaction outcome of what you have chosen or action you take. And you could say, okay, I'm going to construct the reward value for those actions, for that option, just basically summing over all my experiences. So that sounds a nice option, except that your estimate is going to be off if the word is changed. Meaning that you don't want to, so this is looking back in time, you don't want to really past experiences very long time ago affect your how you value things. So probably you want to decay them over time. So you want to have some sort of decay and integration of reward. But what is the time constant for that? It's a big, difficult question. And people have many different ways of actually, different models to look at what is the best or optimal integration of reward outcome over time. So you can think about it, if you are in an environment where things are changing rather quickly, so you see things are good, bad, on average, you want to integrate on a short time scale, yes? This is more optimal. Why? Because you don't want, when certain option is good, you don't want to integrate over the longer history, which is actually the opposite. It makes you lose the fact that this option is recently good. But there is one problem with this integration, which is what you get for your estimate of your reward by weighting the previous reward outcomes like this is that your estimate is less precise. Less precise, why? Because you're just looking at few outcomes. You're integrating just few outcomes. But it's more adaptable. Why? Because if the word change, you're going to detect it and drop your every single time. Okay.
You got it.
It's all right. I'll
Where does it fit? Oh, in here. Okay, good. Next time it drop, I know what to do. Okay. So this is a dilemma here that you try to solve. How to make things more precise? When you make things more precise, you're going to pay for adaptability. So imagine now the environment is not changing so much. So something is good for a while, it was bad before that. You can actually increase your integration time so that you get more precise estimate of what is going on based on more reward outcome. Now you're more precise, but less adaptable. So this is really the core of the problem in learning, that you need to adjust it constantly. There is no way out of this. And I give you another example where this trade-off shows up. The trade-off between how precise you want to be and how adaptable you want to be. You want to be more adaptable, you need to look at the recent outcome. You need to integrate over a shorter time scale. When you do that, you lose on precision. Vice versa. If you try to integrate more, to be more precise, then if the word changes, you're screwed. Because you're actually, what you know about the word is out of date. So now, that's why what I mean by basically you need to adjust your learning. Depending on how the environment is it volatile or stable, you need to have different integration for how your integration time scale, how you're integrating the word outcome. So, so learning needs to be adjusted. Then you can think about two types of adjustment. One is that how much should be the amount of adjustment, how much should be the adjustment, and what should be adjusted. So today I will not talk about this part, basically how you determine the time constant of learning or adjustment, but I talk about what should be adjusted. And again, I put everything in this framework, which makes life easier, which is this adaptability precision trade-off, which we use it to talk about these things, but similar concepts exist. People have suggested similar concepts, but they mean something different. But what I mean is that in the context of learning from reward feedback, that is true about any types of feedback, you are always dealing with this situation. Now, let me go further and then tell you. Okay. So, I'm going to tell you how the learning now needs to be adjusted over time to deal with these two, with this high dimensionality and volatility of the word. So first I will tell you a small, simple framework so you can conceptualize what I mean by these different factors. And then I will show you some experimental evidence for how humans actually adjust their model of the environment in terms of what to learn, not exactly how much to learn. That is a different question that I'm not addressing here, but I'm happy to talk about it if you're interested. And then I will just, at the end, I will show you some plausible mechanism by which learning adjustment can be instantiated in the brain. And at the end, so because the goal of my lab is to, at the end, to get, so we start from behavior, try to explain the behavior, try to come up with mechanism for explaining the behavior, so that we can actually talk about the neural mechanism. And it's funny that we don't do any recording in the brain, but that's our goal. So what we do is that we collaborate with other people who do that. And can include molecular physiologists and also human imaging people. Okay, so to give you an example of what I mean by the model of the word and how that also relates to this adaptability precision trade-off, think about how you learn the value of different types of apples. So you can think, okay, these are different types of apples. Some of them I even don't know the name, but for this talk I actually looked it up. So there is Crispin and Fuji and Gala, whatever, I don't know which one is which. But the point is that when you're a kid and you want to learn about these different types of apples, the only option is you have to eat them, just experience them one at a time, and then after a while you form a value for it, like depending on your taste, and you figure, okay, for this kind of apple, which I think is a golden apple, I assume, what determines a good taste, for example, which could be different for these other apples, etc. So, what is the problem with learning like that? Is that actually it's very slow. Yes, for every damn individual item in the world, you have to experience it many, many times to get an accurate estimate of the value of it for you. So you may die actually before you figure out the types of apples. Forget about other things. Another thing you could do, which is the heuristics that I'm going to talk about, simple learning, is that you basically just think about features of this option. And when you think about features of this, you ignore, these are different types of apple. You try to actually use the color, the crispiness, and size to determine the value. So every time you eat an apple, you ignore, what kind of apple is that. You just pay attention to these features. And then when you do that, you get reward feedback, you update that. So that is basically what I'm going to talk about today, about how you construct a simpler model of the world. It's based on, of course, some assumption, which we call it feature-based learning. You learn about features of options. Or it can be actions. Here, we talk about options mainly, and how that can help you to learn about, to deal with multidimensionality and volatility of the environment. So it should be clear right now that doing this, actually, I can talk about this slide for a while. After. Okay, so I'm fine. Because I can touch on these concepts later, but maybe if I talk about it earlier, it's easier to understand. So, what you can see the difference between these two types of learning, which I'm going to basically, the rest of the talk is going to be about object-based learning, what we call learning by individual items or options, and feature-based learning is that feature-based learning is faster. Yes? Every time you get an update, you can update many features at the same time. You eat this apple, you update the color of it, the crispiness and size of the value for all the apples in the world. But of course, another thing it does is that it reduces the dimensionality of the world for you. So instead of thinking about how many options could exist in the world based on the number of features you have, this space is much smaller. And of course, it comes at a cost. What is the cost? The cost is that this model that you just invented for the world, which you can make it more complex, is not precise. It's going to have problems because, maybe crispiness works for certain types of apple, but not for the other two. For example, I hate green apples, okay? And it doesn't matter how crispy they are, because they're sour, yes? It makes me feel bad. So I cannot generalize the value of crispiness to all the apples in the world. So you can see that this model, feature-based learning, is a little imprecise, or maybe more than a little imprecise. So I tell you again how we can solve that too, but it makes it faster and reduces dimensionality of the world. Okay, so this is the framework. You want to learn dynamic multidimensional world, do feature-based learning or object-based learning, with the definition I just gave you. So we have n dimension, and each dimension has n feature dimension, and each one has n values. So you have colors, 10 different colors of that, and then you have size, and 10 different sizes, etc. You get this exponential problem of the number of individual options that you need to learn. If you learn by feature, all you need to know, of course, you approximate it using some rules, and all you need to know is to learn the n times n. So you see that there is a huge dimensionality reduction here. This problem, basically, people call it the curse of dimensionality reinforcement learning, which is how the hell you deal with this big number here. And there are many different ways to solve it. And here I'm just suggesting that have a learning by features. And what does it give you in the framework I mentioned? So there are three factors that would influence you to go this way or that way. So if you want to do dimensionality reduction, it will push you to go to feature-based learning. If you want to also increase your adaptability without compromising precision, you go that way. I should explain what do I mean by that. And then lack of generalizability. So you make up these rules, but if they suck and they don't work in a certain domain, you have to learn about the objects. So these three factors that move you one way or the other. So What I mean by increasing adaptivity without compromising precision is that in the first example I gave you, if you want to make your learning faster, you increase your learning rates. And I said it will cost you something, yes? You lose precision. When you think about feature-based learning, you can update many things at the same time with a slower learning rate that you could have. So you could have a slower learning rate, but many updates at the same time. And that is basically helps you to mitigate this adaptability precision trade-off in this case or in any other cases. So, is this framework clear? Because before I dump 4 experiments on you. Okay, so experiment 1. So all these experiments are basically the same. The subjects are presented with 2 items. These are colored. Yes.
Actually, so I just had a question.
Yes.
Yeah, I guess about the assumption that less stability in the world necessarily implies that a faster learning rate is better. Because you can imagine
The less is more stable. Yes.
Yeah, exactly. So you can kind of stabilize an otherwise noisy world.
Yes. So if the world is stable, you can slow down your learning rate, and you get a very precise estimate of what is going on.
Right.
So, and then if it's not, so you want to adjust your learning based on the volatility or stability of the world. But you still deal with that trade-off, which is when you increase something, you're going to pay on the other side. So there are ways to mitigate that. And I'm saying that is one way. So you don't need to actually increase. So if the world is changing really fast, you say, okay, I have to update everything very quickly, yes, for options. But I say, no, you can do one more thing, still use features and slow down, don't increase your learning rates or update rates, and then you're still fine. Yes?
There are some fears that there could be multi-scale learning happening, and if I don't know what's the optimal scale for learning because there's so much volatility, it might be actually optimal to learn at multiple scales and later figure out maybe there were longer-term volatilities, although I thought things were.
Yes, so people have been, I think, Peter Bozart, a few other people have talked about multi-scale volatility, and even though they show some results for it, I tend to not believe them because of the experiment that actually we have in our lab, and I see how difficult it is that the people actually captures even one scale. So you could change at different scales. Yes, you could, for example, have let's say color change on the scale of 50 trials, and then change something else on different scales and see whether people can capture it. And we cannot find any evidence for that. So, but yes, there is this idea that you could actually have multiple learning processes at different time scale, and then figure out which one to use. But then you have to solve the problem, which actually is the solution, which is what is the time scale? Yes. If you know the time scale, you don't need to actually run multiple models. So that's a little circular to me.
Not really, because if you're uncertain about the optimal time scale, it's optimal to get multiple.
Yes, but if you have multiple learning rates, yes, then what you are going to do with all the signals you get from these systems, you can say
represented in different parts in the brain. So,
but you have to combine it again. You have to arbitrate at the end. The arbitration problem,
and the decision time. Yeah.
Yes, is not going to be easy. That's why it's not easy to solve these problems. But we can talk about it later. There was a question over there? Yes.
Yeah, just a simple clarification question. So in this framework, is the learning rate the same on all features?
Yes, you could, but you could make them different too. I'm just saying in general, if you choose one learning rate here for object-based learning, you can actually have a slower learning rate for feature-based learning and with the same precision. So you don't have to speed up learning when you're dealing with the volatility of the world or high dimensionality of the world. Because the issue also with the real world is that it's so high dimensional, as I mentioned, there's so many options to learn about that basically you will not have time to update all of this. But again, there are other ideas how to basically generalize, which I think some of the work of Yoel and Niv, also Sam, who's sitting there. There are all this Bayesian framework. Sorry?
NYC gives the paper, because no papers just came out.
Yes. And so that basically you can try to extract and use more complex model to see what is defining the reward value. I'm looking at a very heuristic and simple model, which is feature-based learning, which is just learning by features. Okay, So the experiments, basically we have 4 experiments. One experiment, basically you see we have 4 shapes. So there are 2 color and 2 shapes. Makes you 4 objects. As you can see in this design, the number of features you have to learn and the number of objects you have to learn are the same. So you don't get any dimensionality reduction if you go feature-based learning versus object-based learning. The subject choose between 2 options, they reward feedback. This reward accumulates over time, and at the end of the experiment, they get paid based on the number of correct trials. The reward assignment is probabilistic and is independent. So these are the 4 objects that I mentioned, and these are the reward probability for each one. So red can be giving reward 90% of the time, red square 70%, 30%, and 10%. So we generated different environments. This one we can't generalize it, but for a second ignore this one next to it. So what you see is that red options are better than blue options, and the squares are better than triangles. Okay? And this guy, which is the red square, is the best thing in the world. What I mean by generalizable is that basically you can use features to predict the value of objects. So you don't lose anything if you use feature-based learning here. And what we do is that we are not, every 50 trials approximately, we switch the reward probability on all 4 objects. So there's volatility in what they have to learn. So these are the reward probability, and it switch to something like this, and it switch to something else, etc. What we can study with this experiment is that, so choosing this versus this one, only what it gives you is that it increased your learning speed. Because every time you see an object, if you update 2 features value, you're updating 2 things. While if you just update that object, you're updating 1 thing. So it's faster. So it's basically can help you increase that ability without compromising precision. That is the push that will bring you this way. There is no lack of generalizability because this environment is fully generalizable, meaning that you can use feature value to predict object value perfectly fine. And there's no dimensionality reduction. We have another experiment which is identical to this, but now the way the rewards are assigned to these 4 objects are this way. So now you can see the red, the average reward value of red is slightly better than blue. But the squares are not necessarily better than triangles. So there is no information on the shape, but there is information on the color. Okay? And then the same thing, we switch the reward probabilities between blocks of trials, so the subject have to constantly learn what is going on in the task. Now here basically what you have is that still feature-based learning can make you faster, but then you're paying for it by the lack of generalizability. If you use the value, you think that, okay, red is better than blue, and there is no information there, so if you try to apply it, you will see that you will pay here. When you get to these 2 options, the red is not better than blue. It's only true here. So, okay. Experiment 3 and 4 are now going to be a little more complex because we just have more shapes, more objects to learn. And also what we do is that after running the first 2 experiments, we figure out that actually it's important to ask subjects to give us their estimate of what they think about the reward values. But the rest of the experiment is the same. Now, we have these environments are not fully generalizable. So this would be a generalizable environment. You have these patterns and this shape, and this thing here is the best thing in the world, and this is the worst thing in the world. They more look like this. So you can see that you cannot generalize the value from the features to objects. So on average, certain things are better than the other things. For example, in this case, is the shape has some information in it, but it's not. But pattern doesn't give you any information. And sorry, I forgot to mention now. Instead of shape and color, we have shape and pattern. So here we can look at the interaction between lack of generalizability and dimensionality reduction. One more thing is that in this experiment, we are not changing reward probabilities. These experiments actually are quite brutal for subjects. Okay, we really torture them; they hate them because, and it's a puzzle for me how we do this task so easily in real life. But if I give you this nonsense picture, kind of, subjects don't learn; they don't enjoy it as much because there is nothing in the world that you pick something and tell me, okay, this is the informative feature. Please learn from it. Okay, that's not like that. So you have to figure out what is the informative feature, and then when we give them something like this, there are 8 objects here. One of them, I think this explains there are 8 objects. Basically, they have difficulty learning, and so we have some subjects who don't perform well. So we have what happened? Yes, and in experiment 4, the only difference is that we have more objects. So we increase the dimensionality to see what happens in terms of subject behavior. Now, in terms of the results, this is something you're going to play with later today. So we have these blocks of trials, and then you can basically average, you get the behavior, you can see how the performance changes over time, and also how the probability of choosing better option changes over time. Because this is about subject choice behavior, and this is about the interaction between one probability. So what we do, we can use a fitting procedure based on maximum likelihood estimate, and then you can come up with different numbers, which we'll talk about it later today. Just basically pure log likelihood or AIC or BIC, different measures to compare different models. Probably you have heard about them. And what you can see is that when we fit our subjects in 2 different tasks, we can see that when you look at experiment 1, the BIC is smaller for feature-based learning than object-based learning, which tells us they are most probably doing feature-based learning. When you look at experiment 2, they go on the other way around. Okay? Which basically again tells you what model of the word you're using. So this is our method of looking at detecting what model the subjects are using. And we use different models, around 6 different models. I'm just showing you the best model here. So when you have a volatile environment, you're going to go from object-based learning to feature-based learning. So in the first experiment subject, actually there are only 4 objects, yes? You can't be like how lazy they can be. They could just learn 4 objects, but actually they learn about the features because it's fast. When you introduce non-generalizability, so they can't use the rules that they were using in the first experiment, now they're going to learn about objects. And again, why? Because this rule doesn't work. Experiment 3 and 4, so actually the data you're going to play with is from experiment 3. This is the performance. So, and you can think, okay, this is quite miserable, but if you do the task, you will see that it's not that miserable. This is the optimal you can do, and this is the average over subjects in the experiment. So you get to this value. Now we'll skip what are these things. At these different points during the task, we ask them to give us estimates of what they know about these shapes. And then we use that to infer their learning. We did 2 things. One is that we can just use a GLM to see that and look at, so we know from the structure of the task what is the reward value if you use objects, and what is the reward value if you combine features to predict objects. And then we look at the estimate that the subject gives us and feed it based on this. So what you see here is that overall we can predict better slightly based on these 2 pieces of information. What is the actual reward value and what is the reward value based on features. These are the estimates that the subject gave us. You can account for 20% of the variance. But the other thing is that you can compare the weight of object-based learning versus feature-based learning. And basically that shows you that the transitioning from feature-based to object-based over the course of the experiment. You can see it also differently if you look at the fraction of subjects for which you can feed their data better with feature-based than object-based learning. So as you can see, that fraction also increases over time. I think I said the opposite, but you get it. One more thing, there's one more trick that we use. I think Luke is going to get mad soon because I'm going over time. Oh, okay, nice. Is that, so we have played with different versions of this, and I'm pretty sure some other people have done it too. So after feeding your data, you can look at the average log likelihood over time. And you see where in the experiment you can fit better your data with a given model. And this is basically what is plotting here. So if you look at the fit based on feature-based learning, this is what you get the blue line, and you can see that this is for object-based learning. So what we see is that all this transition that we see from feature-based learning to object-based learning is actually also reflected in how well you can fit the choice behavior. This is not fitting choice behavior, this is fitting estimation that the subject gave us. This is fitting the choice behavior. So you can see at the beginning, actually, you cannot distinguish anything. Of course, at the beginning of the experiment, you can't distinguish anything because even the subject don't know what they're doing. But later on, you can see that they separate, and you can see that object-based learning or feed explains the behavior better. So this is an evidence basically, if you start with multidimensional work, what people are going to do, start learning by features. And then, if the world is not that horrible, they start learning by objects. Slowly they are switching to learning. But experiment 4, we have more objects, and the world is actually more generalizable. So less incentive to actually do feature-based learning. And what you can see is that all these plots are flat, and there's a lack of caption here, but you can see that the feature-based learning is actually performed almost better than object-based learning everywhere in the experiment, which tells you basically these subjects are starting with feature-based learning, and they never switch to object-based learning. So, again, now what I did is that the experiment 4, I'm pushing people more this way. The dimensionality reduction is larger, and the lack of generalizability is smaller. So basically, make them to go here. So what I basically want to show you, and this is just comparing experiment 3 and 4, so you can better contrast them. I think I already explained it. But so they start with feature-based learning. They go to toward object-based learning. They never do that for this one. And I don't know if I could torture them a little more, what would happen. But I'm assuming they would learn more and more about objects. But at this point, this is half an hour through the experiment. They're quite sick of the experiment. So that's why I like monkeys. Because they can't tell you. Yeah. So your experiment is always great. So anyway, this is a summary of experimental data. In experiment 1, when you have generalizable environment and it's dynamic, subject of feature-based learning, so to mitigate the adaptability precision trade-off. When you introduce non-generalizability, now people actually adopt object-based learning. One thing I don't show in this data is that we ran few versions of this experiment, and we are frustrated by not being able to actually make subject to adopt object-based learning. It's very difficult to push them the other way around. Feature-based learning is really good heuristic. Or you can say people are really lazy, but it doesn't matter. So in experiment 3 and 4, I just said what I want to say. So the idea is that this feature-based learning actually provides a powerful heuristic for learning in dynamic multidimensional environment, because it can reduce dimensionality, speed of learning without compromising precision. I have to give you like 2 minutes. Tell me about the model.
About
1 minute. Okay, great. So what you can see basically, you have this issue. So this is the model we have, but you have what we call object value encoding neuron. So imagine you have sets of neurons that they are learning about the value of different things. Red square, red triangle, blue square, blue triangle. So you can learn each one separately, or you can have set of neurons that learn about the redness, blueness, squareness, and triangleness. Okay? And then for this guy, you need to combine their information to know what is the value of red square. This guy directly learn everything. So you can think about it, you could use these guys to make decisions, or you could use these guys to make decisions. But then you have to decide what model you have to weight more or less. So basically, this is just showing how this arbitration happened. And we came up with 2 different scenarios, which both work well, but one of them work better. So in one case, this is just 2 examples where you could solve this, is that you could make 2 different decisions based on each system, and one based on the combination of system. The 2 systems, and then if you get rewarded, so who else was actually saying the same thing, you increase this weight. So if a decision based on single system is the same as the final one and is rewarded, you promote it. Very simple idea. Another way you could solve this task, which we call a hierarchical decision making, because we have to call it something, is that so you have these 2 sets. What you can do is that you can see what is the strongest signal in each system. You choose that, and then you make a decision based on the strongest signal. So you don't arbitrate between the 2. You basically arbitrate between the signals in each one. And then if this was the signal that made the final decision, and was rewarded, you increase these synapses here, you make them stronger, which means the next time you're going to select them more, and vice versa. So this is my last slide, I think. So this is the parallel decision-making learning PDML model. And this is the HTML one. And as you can see, everything almost here is similar. So you can ignore experiment 2 and 3 and 4. In experiment 1, this first model cannot bias itself to our feature-based learning. And there are reasons for that. But this other model can do it. So basically, this HTML model, which is using the best signal in each system to make decisions, it's more consistent with the result. Okay, so this is what I want to tell you about the modeling. So I'm not going to make you play with this model, but if you want, I can send you later. So, and there's of course this issue that other people also have tried to address, is that when you learn about features, of course, there are some features that are more informative and less informative. So there will be a role of attention in terms of what feature you're attending and using to update. And we see that also in our data as well. So you can decrease dimensionality, you can increase adaptivity that compromises precision. Not all the way, there is no way to get out of this adaptivity precision trade-off. And then, so if you wonder, how do you deal with non-generalizability of the word, which is the real thing, is that, so we think that basically you learn features for each domain, for different domains differently. If you do that, you're basically breaking the non-generalizability, and so you can have local rules that are working. So let's say, maybe for vegetables, the color works, yes? And then for certain fruits, you have the color rule for those kind of fruits, and then for another set of fruits, you have a different rule. This way, your subset of rules that you're generating for estimating the reward value of objects is going to be more generalizable. And then it tells you basically how powerful this feature-based learning could be. That's it.
Right, so we have about 5 minutes, but then he's going to come to lunch with us.
Okay.
And then we'll also have a lab, so you have plenty of time to ask more detailed questions too. But if you have we have time for a few questions.
Yes.
I'm wondering about the universality of this adaptability precision trade-off. It seems like an implicit assumption here is that it's a dynamic environment out recurrence. So what I mean by that is, so take serial reversal learning tasks. When animal learns that A is better than B, and then it switches and B is better than A, it does that repeatedly. We know from many experiments that animals will learn that faster and faster. They'll adapt to the switches faster and faster. So that's an example, I think, where they're getting more adaptable and they're getting more precise because their estimates of the word value is getting better.
So that's a good point. So if there's some other rules that you can extract from the environment, for example, is that if the word is reversing, which is the construct of most of the experiment, even this one we're using here, you could use that knowledge basically to actually promote your adaptability. But I agree. So what I'm saying here is that is in the framework of you're not using a model-based approach for the word. So if you try to use a model-based approach, then you can come up with all sorts of things that you can do to improve this. But again, I feel like those constructs, so for example, reversals, they're kind of fake. There is nothing in the word that reverses on certain time scale. Yes? Even if there is reversal, it's going to happen at different. We use this fake construct in our experiment, hoping that subject cannot detect it. And what we have is that their behavior doesn't change over the course of the experiment. We have no evidence for it. It could. But I agree, there's some evidence in probabilistic reversal tasks in rats, namely, that they get better and better over time because they can predict the location that happens. But here we don't see. So, but I don't know, do you agree that there are limited number of rules like that you can make even for the,
The rules that change.
that the rules that you can use to increase your adaptability. Like there's something in the structure of the word that is so persistent that you can use that on top of your learning to help your learning to be more adaptable.
I mean, I think that happens all over the place, but maybe we should have
Okay.
a conversation for another time.
Okay. Yes.
So in this experiment, the trials are all independent of each other. So your reward on trial N doesn't depend any way on what you did in the
an inherent dependence between trials, which is come from the reward schedule. Yes. So we fix the reward schedule. They are independent, but you can use that information for a while. Like 5 trials equal to the reward probably still is true. But then there is a place where reversal happens and everything is screwed. But in terms of, yes, if you have dependency between trials in terms of information, then I mean, the learning model you will have is going to be very complicated. But yes, we are not considering it here. And then what it implies, what it could imply for.
I guess what I was imagining was like somebody goes hunting and then they like go to an area and they like stick a strategy and then they get the animal and they kiss a part of the animal, you know, and then so like, the reward is like the metabolic content of the animal. So there's a whole series of things, and even in a model-free framework where you don't have some kind of model of how the world works, you could just do a kind of a even if you don't have a model-based kind of strategy, you still have a whole lot of other choices which relate to that outcome, and they kind of have different temporal relationships to the outcome. I'm just wondering whether, in that case, the nature of volatility, the considerations of volatility operate the same way.
Yes. Yeah, I agree. It's going to be different. So especially if you consider the correlation, so that basically can resemble some sort of association between something we have seen, like temporal association between what we have seen recently and now, and that can be another piece of information that you can use to improve your performance or learning. Yes, that's not considered here, because this is, when you talk about object-based learning, this is purely model-free. So you just basically just learn about these different things. And then the feature-based learning is a rule-based learning, but it's a simple format. It's not trying to extract anything more than first-order relationship between the features and outcome. But you can think about conjunction of them. So one question we are thinking right now is that, so this is the first step really. So this is ridiculous, simple feature-based learning. And there's object-based learning, which is you learn about everything in the world. So what is the spectrum here? And when, for example, when we start learning about conjunctions of features. So again, if you think about see yourself as a child trying to learn what is going on in the world, basically you will see that all those things show up. So I would relate the learning about the conjunction, something similar to the temporal correlation or relationship between what you have experienced. And you can use it as another piece to improve your learning. Yes.
So why don't we thank Alireza and let's go get some lunch.